Great. So it's a pleasure to welcome Clarice Poon from the University of Cambridge, who will be talking about multidimensional sparse super resolution. Please.
Thank you for the invitation. I'll be talking about joint work with Gabriel Pérez. So the problem that we'll be considering is as follows. So we'll work on a domain X, which is contained in either Rd or in the torus of dimension D. And what we want to do is we want to recover a Redon measure from Hilbert space measurements. So these are my measurements Y here. So we have a sampling operator phi, which takes Redon measures to an element of a Hilbert space. And your sampling kernel phi, little phi here, takes elements in our domain to Hilbert space elements. And the W here is the additive noise, which comes from the acquisition process. So in this talk, what we're going to be interested in is we want to recover discrete measures. So measures of this form, a superposition of Dirac masses, where A times delta Z means a Dirac at position Z with amplitude A, and they're also called the D spikes. So just to give you some examples of where this is of interest. So the first example is in, say, astronomical imaging, where what you observe where your sampling operator is a convolution with some kernel phi here. So quite often you may take this phi to be the low-pass filter, so this sinc function. And in classical resolution theory, the smallest minimal resolvable distance between two spikes is generally thought to be 1 divided by Fc, this cutoff frequency that determines your sampling kernel. And essentially, if you have a method which allows you to resolve two spikes while sampling below this Rayleigh length, then you say that the method achieves super resolution. And if you're working on the torus, you may consider the convolution with this Dirichlet kernel. And note that if you observe convolution with this Dirichlet kernel, then you're observing all the Fourier frequencies of a measure up to some cutoff frequency, Fc here. And of course, to model acquisition blur, you may consider the Gaussian kernel as well. So the second example that I would like to mention is neuroimaging. So in MEG or EEG, you would want to estimate point sources inside some domain when you're given measurements on the boundary. And so the Hilbert space measurements now live in L2 of the boundary. Okay. And the third example that we'll look at eventually is in machine learning. So in machine learning, you may want to fit a probability distribution to your given data. So in this case, you want to recover parameters AI and ZIs, and what you observe is then a mixture of elementary probability distributions. And then W now accounts for your sampling scheme, so how you sample your data. And in a simple setting, in one dimension, you may consider the case where you have a Gaussian mixture model. And what you want to then do is recover the means and the variance of a Gaussian mixture distribution here then. Okay. And the Hilbert space then is LT of R. And the interest of the domain is R cross the positive real line, which models the mean cross the standard deviations. So these are three examples that we'll look at. And to deal with this parameter estimation problem, there are lots of different methods. So one particular type of method are Prony-type methods, and these are generally root finding algorithms, and they are non-convex and non-variational. So some examples are music, esprit, finite rate of innovation, and many others. And this talk is not going to be about a comparison between these different methods, but instead we'll look at one particular type of method. So the B-Lasso formulation. So this is the least squares total variation regularization approach, where this is the total variation of a measure is defined like this. So if I have a discrete measure, then the total variation of this is nothing more than the L1 norm of my amplitudes. And if I have a measure which has an L1 density, then this total variation is nothing more than this Lebesgue L1 norm. So this is really just a generalization of L1 regularization. And we've got a parameter lambda here, which you generally choose linearly with respect to the noise, as we saw in the last talk. And as lambda goes to 0, you end up with this constrained minimization problem. And I'll call this problem P0 of y, where y are the measurements, and I'll call this P lambda of y, where y are the measurements. So typical questions that you may ask about total duration regularization now are, so for example, what conditions should you, under what conditions can you recover a measure m0 from your measurements 5m0 with no noise when you solve this exact problem? And if you can do this for small lambda and regularization parameter lambda and small noise, are the solutions of this regularized problem somehow close to the true solution m0? So the B lasso has been around since the 70s, and it was pioneered by geophysicists, and it later became mainstream in signal processing due to the work of David Donohoe. But the work that really kind of revived all the mathematical interest in this problem in the recent years was really due to Candice and Fernandez-Grande in 2012, where they showed that you can have exact recovery of the P0 problem if the minimal separation distance between your spikes is on the order of 1 divided by fc. So this is for the case of Fourier sampling, and fc is the cutoff frequency. And so in a sense, if you're trying to recover spikes of arbitrary signs, then you can't really hope to go below this Rayleigh limit. So with B lasso, you don't really have super resolution. But there was also another interesting result by Castro and Fabrice around the same time, which shows that if you now restrict your problem to only recover positive spikes, then you can recover any n spikes provided that all your amplitudes are positive and the number of samples, so cutoff frequency you need is fc greater than or equal to n, the number of spikes. And so the interesting question now is, at what rate should your signal to noise ratio, so 1 divided by signal to noise ratio, drop to 0 as a function of the spike separation distance, such that you still have super resolution of the spikes? Okay, so you can always recover n spikes, but what happens when there's noise? Do you still recover n spikes? And this question was addressed in the one-dimensional case by Denuel, Duval, and Pele recently, where they showed that in the 1D case, the answer is that you will have stable super resolution provided by that the 1 divided by S and R scales like t, the separation distance, to the power of 2n minus 1, where n is the number of spikes. So I'll say more about this later on. And what this talk is going to be about is about a 2D, what happens in high dimensions. How should your signal to noise ratio drop? Okay, so just a mention of what kind of results there have been in high dimensions. Well, there actually haven't been that many in the case of super resolution. And I'll just mention this recent result by Candice and Morgenstern, where they considered a convex setup, but this was discrete n on the grid. And so they kind of showed a L1 error on the recovered x hat here. And the error is scales like delta the noise, and this is what they call the super resolution factor. So m is the discretization, fc is cutoff frequency, and n is number of spikes. But here is a kind of integral estimate. It's not really so clear how it generalizes to the gridless case in infinite dimensions. And the other work I'll mention is this older work by Sharam and Milifar, where they didn't consider any particular algorithm, but this is a statistical decision theoretic or information theoretic point of view, where they essentially showed that the minimum resolvable distance between two spikes should scale like t to the power of 4. So 1 divided by SNR should scale like 2 to t to the power of 4 if you were to be able to resolve two closed spikes. Okay. So that is the backdrop to our problem. And so now in this talk, what we'll do then is we'll look at recovering a positive measure, positive discrete measure. And the questions that we're going to address are as follows. How should my noise and regularization parameters scale relative to the separation distance between my spikes, such that, firstly, our regularized solution has a unique solution, and such that we can recover exactly n spikes. And moreover, what we want is that what we recover, the amplitudes and the positions, should converge to the true positions and true amplitudes in a continuous way as our noise and regularization parameter go to 0. And when we're able to have this, I'll say that the problem is support stable for this particular measure. And ultimately, what we want is a condition which is a kind of dual certificate condition that we see in the previous talk as well, which is easily checkable, at least numerically, to let us determine when you do have stable super resolution and when you don't. And we make some progress towards this goal, as you see in the end. So just to give you some background on dual certificates, so how we should approach this problem. So firstly, as we saw in the previous talk, a discrete measure, M0, is a solution to the exact B-Lasso minimization problem if and only if the source condition is satisfied. So, for example, if M here is the measure with these directs, then what you want is that you want there to exist some function eta, which is the image of phi star, such that eta is bounded in absolute value by 1, achieves the value minus 1, where the signs of my spikes is negative, achieves the value plus 1, where the signs of my spikes is positive. And as mentioned in the previous talk, many people have studied the source condition. And when you have the source condition, then you can derive some kind of integral stability estimates. So typically, you will have stability guarantees if there exists some dual certificate which is non-degenerate, meaning that away from the support Z, you have absolute value strictly less than 1. And you also want some control on how quickly you go away from 1. And to get this control, typically you would put some constraints on the Hessian of your certificate at your support points. So where you have you achieve the value 1, you want this to be negative definite, and where you achieve the value minus 1, you want this to be positive definite. Okay. And you can have control on, say, the Bregman distance, the total variation of your measures, and in the case of Candace Fernandez-Granda, they showed you get control on the L1 of your recovered error of your recovered measure convolved with some high-pass kernel. Okay. But the problem is that these kind of estimates don't really tell you anything about support stability. Do you recover exactly n spikes? Okay. And it turns out that if you want to look at support stability, there is actually one specific dual certificate that you should be looking at. And that dual certificate is the dual certificate with smallest Hilbert space norm here, the minimal norm certificate. And this was studied in this nice paper by Duval and Pele in 2015. And what they showed is that if this minimal norm certificate is non-degenerate, then provided that your noise and your regularization parameter are sufficiently small, so small than some small constant, then your regularized, your B-Lasso problem will have a unique solution, which consists exactly of n spikes, and the recovered spikes will converge smoothly to the true spikes in true positions as your noise drops to 0. And in the case where this certificate saturates, so achieves absolute value plus 1 or minus 1 at values other than the support Z, then you will have no support stability. So meaning that you will always have the very small spikes at the points where you saturate. Right? And so in some sense, if you want to study support stability, this is the certificate to study. And note also that it is actually the minimal norm certificate that gave you the level set stability that you saw in the previous talk as well. So for geometric properties, this is the guy to look at. So in practice, these dual certificates are difficult to analyze, essentially because of this constraint that your L-infinity norm has to be bounded by 1. So this is a nonlinear constraint. So quite often what people do instead is you would study a vanishing derivative certificate. So all I've done here is I've thrown away my nonlinear constraint of being absolute value bounded by 1, and I replaced it by this derivative constraint, which is necessary. Right. Well, actually, I say I, but this was Bonson and Gabriel. Anyway, so, okay. So then, if this pre-certificate now is non-degenerate, then it coincides exactly with the minimal norm certificate. So then you can guarantee support stability in the small noise regime, right? And the nice thing about doing this is that you can simply write all these these conditions down as a linear system. So in particular, this linear system now is determined completely by this correlation operator defined like this. Okay. So to compute this guy, all I have to do is to invert a linear system where the size of this linear system is q squared and q is the number of constraints here. So I can easily compute this, check if it's a real true certificate, then that tells me whether eta 0 has support, will give me support stability or not. And when you look at positive spikes, then the interesting thing to know is how do these certificates behave as the spikes converge to 0? So this is what was done in the 1D case by Denoel, Duval, and Paley. And so the questions you may ask are, do these certificates have a limit? And does such a limit certificate characterize non-degeneracy properties of the pre-certificates when t, the separation distance, is small? So this is a picture of a deduced certificate as t goes to 0, and this is the limit you get. And what they showed is that as t goes to 0, these pre-certificates will converge in L-infinity norm to this guy here. So you have to take value 1 at 0, and then at 0, your derivatives all the way up to 2n minus 1 is equal to 0. So this essentially just follows from Rolle's theorem, okay? Because you always have one vanishing derivative at each of these points. And now what they showed is that if eta w is degenerate, non-degenerate in the sense that its absolute value is strictly smaller one where x is not equal to 0, and its 2n's derivative at 0 is strictly negative, then this implies that when your separation distance t is small, your pre-certificate with respect to tz will also be non-degenerate, which means that you have support stability. And essentially, what you want for this to hold is that you want the regularization parameter to scale like t to the power of 2n minus 1. So that would be the SNR scaling that you would need. And so it was proved, so they were showed that indeed eta w will be non-degenerate in the case of Gaussian convolution, and also for the Laplace operator. And more recently, we also looked at the Dirichlet kernel, so the Fourier sampling case, and in the case of where the cutoff frequency is exactly n, so the limit case, we're able to write down an explicit form for the pre-certificate eta v and the limiting certificate eta w. And in this case, you also have that they are non-degenerate. So support stability is reasonably well studied for positive spikes case in one-dimensional case. So this talk is about the 2D case. And note that in the one-dimensional case, as your certificates converge, actually the limit does not depend on what these positions z were initially. You just need a 2n minus 1 derivative vanish at 0. But in the high-dimensional case, what is more difficult is that the limit of your pre-certificates now depend on the node configuration. So this is the pre-certificate in the case of 3 spikes here. And along here, I'm showing as the spikes converge to 0. And this is in the case where they converge when they are all aligned along one axis. So you see here that the limit is very different. And what this intuitively tells you is that whether you have support stability and super resolution is now going to depend on the node configuration, on how they converge to each other. And so the first task we wanted to do is to basically characterize what this limit of all my pre-certificates should be. And intuitively, what we want to do is we want to identify some polynomial space at z, which depends now on the node configuration, such that we can define our limiting certificate in this way. So as usual, you would constrain that you take the value 1 at 0, and the derivatives that you should vanish at 0 would then depend on this polynomial space. So in the 1D case, this polynomial space is simply taken to be the polynomials up to degree 2n minus 1. And note that if we're able to do this, then it is again very easy to compute eta wz. So we just write down all these linear constraints as a linear system. And this linear system can be constructed entirely just by looking at the correlation operator and its derivatives, which are defined by some basis of this polynomial space defining this guy here. So first point is that actually there is a link to polynomial interpolation in terms of what this space should be. So this is what the pre-certificate eta v is at tz. And if I tailor expand each of these guys about 0, then what I end up with is this expression here, where htz is the Hermite interpolation operator applied to a polynomial whose coefficients p here are these guys here, the derivative of your potentials to eta evaluated at 0. So what you essentially want to do is you want to look at the limit of your Hermite interpolation operator as t goes to 0. And so to work out what the space as z should be, this let us look at Hermite interpolation in the multivariate setting. So some definitions and notions from Hermite interpolation, polynomial interpolation. So the classical Hermite interpolation problem over a polynomial subspace S in pi d, so pi d denotes polynomials in dimension d. It looks for a polynomial p, which is in S, which is the solution of these equations. So the derivative of your polynomial evaluated at a particular point is equal to a given value, C alpha r, for all derivatives up to order kr here. And we say that this problem is regular for these derivative functionals, f alpha r, if there exists a unique solution in this polynomial space for each given c here. And if there does not exist a unique solution, then you say the problem is singular. So in 1D is very straightforward so the question is how do you choose this space as such that you have a regular Hermite interpolation problem. So in 1D is very straightforward. You can always choose S to be the canonical polynomial space, where n here is the largest degree of the polynomial space and is simply the number of interpolation conditions that you have. But some issues in high dimensions are as follows. So firstly, if you want to take a canonical polynomial space, then what you need is that the dimension of this polynomial space should equal the number of constraints you have. And this is a problem because, say, in 2 dimensions, if you want to do Hermite interpolation up to the first derivative at 3 points, then actually you have 9 constraints. But the polynomial space of size up to degree 3 is of dimension 6, and of degree 4, this is of dimension 10. So you don't have this exact match here. And the second issue is that even when you have this exact match, so in the case of Hermite interpolation up to degree 1 at 2 points, then you have 6 constraints. This matches the polynomial space up to the size of polynomial space of degree 2, which is also 6. But actually, this particular choice will be singular for all choices of Z1 and Z2. So this is essentially why multivariate Hermite interpolation is a little bit tricky, because you have to really think about what the space should be. But it turns out that the space we need was exactly the least interpolated space constructed by Debout and Ron in 1990. So what they did is that given any set of linear functionals f, they introduced the least interpolant space, LF, and this is actually the least degree space, which is regular, given any polynomial s given any polynomial space s leading to a regular. So this is the least degree polynomial space that will give you a regular problem. So if I have any polynomial space s leading to a regular interpolation problem, then I will have less or no greater, the number of low dimension elements in S here will be no greater than the number of low dimension elements in LF here. And the space they came up with preserves many natural properties such as scale invariance, translation invariance. This is in some sense continuous with respect to the locations of the nodes we're interpolating. But the key point is that this is always well defined, and it is always constructible in finitely many arithmetic operations using Gaussian elimination. So this is how the space is defined. So the least term, g down arrow, of a real analytic function, g, is essentially the smallest degree homogeneous polynomial that I can pull out of this guy here. And for linear functional f acting on the polynomial space, pi in dimension d, you can define the formal parallel series of gf in this way. So this is the polynomial with coefficients f evaluated at the polynomial x to the power of alpha divided by alpha factorial. And so given any differential form, you can define this exponential space of your functionals. And then the least interpolant space is then the span of the least terms of the guys that are in the exponential space. And this is the least interpolant space. So just to give you an example of what this looks like, if you think about the Hermite interpolation up to the first derivative at these points, 0, 0, and 0, 1, then you have 6 linear functionals. The exponential functionals are simply these guys here. And essentially, then this least interpolant space is spanned by 1, x, y, y squared, and y cubed. And if you like this, you can kind of see when you try to work out this space from this space, that the way to do it is simply write down all these guys as a van der Waals matrix, and then you do Gaussian elimination, and you take the least terms that you get out of your Gaussian elimination matrix. But the key point is that this guy always exists, and we can compute it numerically. So the first result is that given any points z, any n points z in x, and if we let Sz be the least interpolant space associated with Hermite interpolation up to the first degree at z, and we'll assume that this space here is of dimension 3n, which is this dimension of this least interpolant space. And then we can define eta w in this way, where the derivatives that you vanish at 0 is now determined completely by your least interpolant space. Then in this case, your pre-certificates, PVTZ, and your so this is a pre-certificate, so phi star of PVTZ is eta VTZ. So you have convergence to this limiting certificate in this way, as t goes to 0. And what this assumption is here essentially comes from the natural requirement that your sampling operator should be somehow injective on the solution manifold, which is quite a natural requirement, say, in compressed sensing as well. So we now know what the limit of these pre-certificates are. And just a comment about this, this assumption here. So in the case where phi is a convolution operator, so it is of this form, and if L is the smallest integer such that our least interpolant space is contained in the polynomial space up to degree L, and the Fourier coefficients of our kernel phi evaluated at alpha on this grid are non-zero, then that condition will be satisfied. So this condition is, in a sense, a condition on the number of Fourier frequencies that you should observe. And moreover, the size of this polynomial space, so this L here, the degree is always no greater than 2n minus 1. And actually, in some non-trivial cases, you can also show that L here could sometimes scale like square root n as well. So when it scales like square root n, this essentially gives you a linear relationship between the number of spikes and the number of non-vanishing frequencies of your sampling kernel phi. And actually the worst case happens only when all your spikes are aligned along some axis. So now that we have the limiting certificate, the question is, what do we do with it? And the first point is that it is completely necessary for this limiting certificate to be a valid certificate, so to have absolute value bounded by 1 if you were to have support stability. So in particular, if there exists some t distances, tn, which goes to 0, an and zn, such that the position zn goes to z0, and m, and the measure an, tn, zn is support stable, then it's necessary that your limiting certificate has absolute value bounded by 1. So what this means is that if I compute my limiting certificate eta w here, and I see that it takes value greater than 1 at some point, then what this means is that given some noisy data, however small I make my noise w to be, and however choose my regularization parameter, in principle, your regularized solution will always produce solutions with additional small spikes. So you cannot have support stability if this guy here is not a valid certificate. So just to show you some pictures of what this limiting certificate EW looks like. So this is the example where we look at Gaussian convolution. And what we observe numerically is that EW is always a valid certificate for any number of spikes and any spikes configuration. And intuitively, what this tells us is that we should be able to hope for super resolution when your SNR is large enough. So this is the certificate when, in the case of 2 spikes, and so my spikes are shown in red here, and they're converging along this dotted red line. This is the case of 3 spikes, 4 spikes, and 5 spikes. And something to observe is that actually this limiting certificate is much better behaved than what we really impose. Because if you go back to the 3 spikes case, then the least interpolate space is actually of dimension 9. And this is contained in the polynomial space of degree 3. And the size of this space is actually 10. So when I define this eta w here, I did not impose that all my third derivatives vanish at 0. And if they don't all vanish at 0, then intuitively, then actually what this should mean is that you should escape 1 near 0. But this doesn't happen. And essentially, the reason is that for a convolution operator, you actually have some symmetry in the correlation kernel. And so what we can then prove is that all the odd derivatives of eta wz here will be equal to 0 at 0. So in some sense, it's much better behaved than what we impose. Going on to the next example. So this is of neuron imaging, and the domain we're working on is the unit disk, and we are observing measurements on the boundary of this disk. And to model MEG, what will take the kernel to be this guy here. So this kind of models a decaying signal away from the point sources. So, and we're looking at clustering about the point 0.4 and 0.3. So what we observe is that eta w is always a valid certificate when all the spikes are aligned. So in these 3 cases, they're valid certificates. Oh yeah, by the way, sorry, the color scale is going from negative values, blue, to plus infinity, red. And yellow means 1. So if you see colors between blue and yellow, then that's good. If it escapes above, like this one, then that's bad because you're taking values above 1. So these 3 cases are, we have a valid certificate, but what we see is that when you have non-aligned spikes, then actually eta w is not a valid certificate anymore. So what this means from our previous result is that in the presence of noise, you can't superresolve 3 closed spikes in the case of neuroimaging. And for our last example of Gaussian mixture, so here I'm showing you again a plot of the certificates. And so now we're trying to recover the mean and the variance. And the y-axis now is the mean, and the x-axis denotes the standard deviation in our space. So what we see now is that actually when you have more than 3 spikes, then the certificate is never a valid certificate. And when you have only 2 spikes, it actually now depends on the configuration. So these 2 are actually not valid certificates, and these 2 are valid certificates. And so what we see is that when the variation in the means that we're trying to recover is no greater than the variations in the standard deviations that we're trying to recover, then you have a valid certificate. So what it says is that you cannot hope to super resolve using B-lasso, mixture of 2 Gaussians, when the variations in the means is too large. And I'll show you a numerical example of this later on as well. So now looking at this limiting certificate, we are able to say whether there is a negative result or not. And this last result I want to show you is on the positive result. So now we're looking at a special case where we're trying to super resolve a pair of spikes of this form. And the limiting certificate is now defined by these constraints. So it needs to take value 0 at 1, and you vanish the first, second, and third derivative along the direction dz. So dz is z1 minus z2, the direction along that your spikes are aligned. You vanish the derivative, the first derivative along the orthogonal direction, and you also have that this mixed derivative vanish. So this is the definition of e to wz. And we'll now say that e to wz is non-degenerate if it takes value strictly less than 1 when it's not on the origin, and that this matrix of derivatives is negative definite. So if you want to impose that this holds, then actually when I do look at the Taylor expansion of this guy, then these are the derivatives that naturally pop up. So these should be the first derivatives I somehow need to control, such that I am strictly smaller than 1 near this port, sorry, near the origin. So our final result says that assuming that our limiting certificate e to w is non-degenerate, then there is this constant t0 and c0 such that for all distances t between 0 and t0, and all regularization parameter lambda and w in this ball of size t to the power of 4, our B-lasso problem will have a unique solution. We will recover exactly 2 spikes, and moreover, these spikes evolve in a continuous way to the true spikes. And finally, we have this error bound between our recovered spikes and our true spikes. So the signal-to-noise ratio, the size of W, for which we have super resolution, stable super resolution now, is on the order of separation distance t to the power of 4. And note that this scaling agrees exactly with the statistical bounds that Sherem and Millefeld came up with, computed. And note also that there is an additional, so in comparison with the 1D result, so the 1D result have t to the power of 3 here, whereas we have t to the power of 4. And that's essentially coming from the fact that the configuration of your positions matter. So some quick words about how we managed to get this result. So one of the tools behind this result is that if e to w z0 is non-degenerate, then provided that I have given any certificate eta, which is sufficiently close to my limiting certificate, this would mean that eta is also non-degenerate. Okay, so if I define any certificate using the standard pre-certificate conditions, and this is sufficiently close in L infinity norm, and all its derivatives are also close to those of e to w, then this is non-degenerate. And so if this is non-degenerate, then immediately from the results of Vincent and Gabriel, we already know that our B-lasso problem must be support stable. And so the only question remaining is how small should lambda and the size of our noise be such that we have support stability. And For support stability, we want that our recovered positions and recovered amplitudes evolve in a continuous way, smoothly, to the true positions and true amplitudes. And to construct this C1 mapping, what we did is that first, if we simply consider the first order conditions of our bilateral problem, then we know that MATZ is a solution if and only if this source condition is satisfied. So now if I drop the L infinity constraints here, I can simply write this down as a linear system, where this matrix gamma here simply encodes the fact that this guy here valued at point Z needs to take value 1, and this guy here evaluates at the point, and the derivatives of this evaluated at point Z should take value 0. Right. So then I can simply write this. So all I've done is I've rewritten, encoded this as a function, f of tz, ft, with input a, z, lambda, and w. And so to find the candidate solution, all I really need to do then is to find u and w such that ft of uv is equal to 0. And note that if I plug in the true solutions, the true amplitudes and positions, and noise and regularization parameter 0, then this is already equal to 0. So to construct this map, what this suggests is that I can simply essentially use the implicit function theorem to construct this guy here. So then I have a function which takes a small neighborhood in the space lambda w to the solution space u, and then all I needed to do was simply, all you have to do is simply work out the size of this neighborhood on which this function is well defined. And the last thing then you to do is to simply check that the solutions that you map this to is really a solution of this problem here. And this essentially follows from the non-degeneracy transfer result that I showed before, because actually we can show that this guy here, where A and Z is the output of GT, is close to e to w z0, and therefore it must be non-degenerate. Okay, so just some comments. This result naturally extends to the case where all our spikes are aligned along some direction, dz0. And so under this natural non-degeneracy condition, the SNR scaling then becomes t to the power of minus 2n. But unfortunately, our result actually doesn't extend to the case where you have more than 2 spikes. And essentially the reason is because of the fact that we actually vanish additional derivatives that we didn't impose. So this nice fact that I mentioned before about convolution kernels. So in particular, if Z consists of any 3 points which are not collinear, then I can actually define a new certificate here with the same conditions as we had before in pre-certificates, plus this additional condition that phi star p evaluated at tx is equal to 1. And what happens is that actually this has the same limit as when you don't have this constraint here. So the point is that the non-degeneracy transfer condition doesn't hold here, which is why we're not able to extend it to more than 2 spikes. So just because something is close to this does not mean that it necessarily has to be a non-degenerate U certificate. So let me end by some numerical examples. So to solve this bilateral problem, there are many ways of doing it. So there's the Lazaire hierarchy of that essentially Candace and Fernandez-Grande used in the paper, and the other approach is this Frank-Wolf method with improved non-convex updates, which was proposed by Bredis and Picker-Reinen, and also recently in this paper by Van Recht. And the way this algorithm works is that it alternates between these 2 steps. So it first does a matching pursuit step, where you find a new position x tilde, L plus 1, which is the argmax of this function, which is a candidate certificate. And then you take your new amplitude, AL plus 1, to be lambda times this guy evaluated at my point x tilde L plus 1. And then once I've got these two new points, you essentially do a local non-convex minimization to locally improve on your positions and your amplitudes by solving this non-convex minimization problem. And we solve this using LBFGS. And after doing this, your new measure then is taken to be this guy. So you have improved positions and amplitudes plugged into here. And you iterate and you terminate when this guy here becomes a valid certificate. So some numerical observations that we had is that we actually always reach convergence in a finite number of iterations when the limiting certificate E to W is non-degenerate. So this is the output of the algorithm. So what we did is that the measurements now are taken to be y of phi of some measure that we want to recover, and we scale our noise linearly with respect to the regularization parameter lambda. So the noise is taken to be phi of some other measure tilde m, where tilde m is of this form, so it's 20 Diracs, whose positions are chosen at random, and the amplitudes are white noise with standard deviation 10 to the minus 3. So this is in the case, the output in the case of Gaussian convolution. So in the background here, I'm showing the limiting certificate, and the foreground, so the red part, shows the positions of your reconstructed measure. So blue stands for regularization parameter lambda equals 0, and red is when we get to lambda max. So what you see is that what you recover, so the parts of the solutions evolve continuously as predicted by the theory. And this is the same thing but for the neuroimaging case. So this here is covered by theory, this here is not, but nonetheless we do observe that when E to W is non-degenerate, you still have this nice support stability property. And I also mentioned that when your limiting certificate E to W is degenerate, so it takes a value greater than 1, then you would not have support stability. So this is the example of a Gaussian mixture. So the background here is again E to W, and the positions of M0 that we're trying to recover in black dots. And this here is the output of the algorithm. So the background is E to L, that certificate constructed by the Front-Wolf method. And these dots here basically show the positions recovered of the recovered ML. So the black dots are the exact positions, and the dark blue dots, so here and here, is what you recover, and the amplitude of them is proportional to the size of this dot. But what we also observe is that you also have these additional dots here. So the light blue dots indicate the support of ML, which have very small support. So these small dots actually are required to force this guy here to have value less than or equal to 1. And this is something that doesn't happen for E to W. And numerically, in this case, then we don't observe any finite convergence. Convergence finite number of iterations, and you see that the algorithm always inserts very tiny spikes to force this to be less than or equal to 1. And a similar thing in the case of neuron imaging, where we're trying to recover 3 spikes. So we have a non-valid certificate here. And again, you recover very large amplitudes near the true positions, but you also recover a lot of additional small spikes, as shown by these light blue dots here. So that's the end of the talk. Our paper is on arXiv. So previous studies have highlighted the importance of looking at pre-certificates analysis if we want to study support stability, so any kind of geometric stability. And what we've done in this work is we characterize the limit of the pre-certificates as the spikes converge to a limiting point. And looking at this limit, we know that it is necessary for this limit to be a valid certificate if we want support stability. And we were able to, by looking at this limit in the 2 spikes case, this also gave us a precise estimate on how the signal-to-noise ratio should scale as your spikes converge. So some things that we're currently looking at, we're looking at the study of other certificates for different stability estimates. So what you see is that in the case of, say, Gaussian mixture, you don't have support stability when the variance in your means is too large, but you may have some kind of integral stability. So it'll be interesting to look at other certificates and look at the limit to see what you can say about stability in the case where you don't have support stability. And yeah, another interesting direction that we're looking into is also subsampling. So where instead of just convolution with some, say, Dirichlet kernel, you may subsample your kernel. So thank you for your attention.
Questions? Michael.
Okay, so I actually have like two questions. The first, maybe it's a little related to what was going on with the subsampling, because in your theory you kind of assume that you're measuring, like the continuum.
Yes.
Yeah. So how does I mean the theory hold up? Let's say if you are putting sampling, and my other question is, it's very interesting because there's this kind of statistical bound. I think of Milan Farr. I think they may be using Kramer-Rao.
Yeah, they are.
And I think what your results tend to suggest that actually, because the Kramer-Rao doesn't tell you how to do.
Yeah.
Here you have an algorithm. Okay, so that suggests that the algorithm, can do as well as
Yeah,
the
exactly.
optimal limit.
Yes.
Yeah.
And with regards to your first question, if you're taking convolutions with the Dirichlet kernel, then that's equivalent to taking Fourier samples at integer points. So there you have a finite number of samples.
Because there's a very direct application. Actually, it's your slide 24. There's a Nobel Prize associated. No, it's a super resolution microscopy. Like they're using Gaussian, and they try like to detect with super resolution the fluorophores in this palm microscopy. It was the Nobel Prize maybe 5-6 years ago.
Okay.
And there's actually lots of work, so it's very interesting. And actually they try to put themselves in a scenario where they just have one spike, okay?
Yeah.
But then then you need to image very long. And so they would like to go like in a sort of a high density scenario where you could have several spikes, but they're little too close with respect to the point spread function of the microscope. And actually your analysis, I think, is very relevant.
Yeah, thank you.
Mike?
Yeah, so of course the Nobel Prize got it by using chemistry rather than mathematics.
Actually, there was an algorithm that was doing correlation with Gaussian.
Yeah. But they got them to switch on and off by using chemistry.
Yeah, of course. That's
The different configurations of your spikes presumably make it harder or easier to super resolve. Do you have a feel for what are the best/worst configurations that will make it? So what would be the sort of simulation scenarios that you want to avoid because they'll be too optimistic, and what ones would actually really illustrate the worst case that you can expect to see?
Well, that would depend on a case-by-case scenario, right? So, for example, in the case of Gaussian mixture, it depends on whether this angle here is greater than pi divided by 4 or not. So in these cases, you cannot super resolve. These two cases you can. So for every single operator that you have, you would need to then do analysis. So there's no one.
There's no easy. No. Okay. And a second question on the Frank Wolf algorithm you're using. Are you imposing non-negativity? Because I think that's a more general. I don't think it necessarily imposes non-negativity on the coefficients, is it? On the.
You mean here when we're
Yeah.
doing? I don't know. off the top of my head, we just use an off-the-shelf.
So I was just wondering whether you can, I mean, there's things like there's non-negative matching pursuit, so I don't know whether it
You mean whether we use non-negative matching pursuit or
does,
standard?
or yeah, so I mean, does it gain anything to actually incorporate the non-negativity constraint?
Short answer is I don't know, but I don't think we actually think about it, I don't think we impose non-negativity here explicitly.
So where you see the case, so you had the neuro case where you had lots of little small spikes. Are any of those? Do you ever see any of those being negative? If that's the case, you might be able to improve.
Yeah, I think these tend to be spikes of extremely small amplitude, which are positive tend to.
Okay,
So, yeah.
that suggests that it's not going to help. Okay.
Okay, I think it's time for coffee break, so we can do more questions in the coffee break. So let's thank Claris again.